Something else that's going to be very helpful to you is being able to understand and draw distance time graphs, velocity time graphs, even acceleration time graphs. Now, if you've already done some calculus, what I'm going to say here won't be exciting and new for you. You've probably thought about this already. Let's start with distance time graphs. What I mean by that is, let me get a better pointer. This is the distance, this is the time. A distance time graph has distance against time. So this describes the motion of an object. It's going from distance 0 away. Over the first 4 seconds, it moves to 30 metres away. Over the next 4 seconds, up to 8, it's not moving at all. It's the same fixed distance, 30 metres away. Over the next 2 seconds, it moves further away up to here, 60 metres away. But think about this graph carefully. Have a look at B. It's not moving at all. What can you say about the gradient of the line there? Well, the rise is 0, the gradient is 0, and the speed is 0. Now have a look at A. In this section, it moved 30 metres over 4 seconds. So its speed would be 30 over 4, 30 metres divided by 4 seconds. But that's the gradient of that line. Look at the gradient. Rise over run. 30 over 4. The gradient of this line at any point gives you the speed at that time. For a distance time graph, the gradient is the speed. Okay, what about a speed time graph, or might be a velocity time graph? Here's the speed, metres per second. Here's the time. Again, have a look here. I'm going to label these sections A, B, C, and D. Have a think about this. In section A, the speed increases from 0 to 30 metres per second, and it took 10 seconds to get there. What is that going to refer to? At section B, it was moving, the line is flat, but it was moving that whole set of 10 seconds, from 10 to 20, it was moving at 30 metres per second. And section C, the speed increased from 30 metres a second to 45 metres a second over that 5 seconds. At section D, it didn't go back to where it started. It slowed down from 45 metres a second all the way to not moving at all, and it took 5 seconds to do so. Now think about that. At B, the velocity, the speed wasn't changing. It wasn't accelerating, and its gradient is 0. And have a look at A. What's the gradient at A? The rise was 30 metres a second increase, and the run was 10 seconds. So the gradient, rise over run, is going to be 30 metres per second divided by 10 seconds, which is going to be 3 metres per second per second. That's acceleration. The gradient of this line, wherever it happens to be, is going to be acceleration. Notice at D, the gradient is negative and it's slowing down. The acceleration is negative because it's slowing down. But we can do more than that. Let me have another look here. Just rub that out. So now have a look. At this section B, let's start again with the one where the speed is constant. Over these 10 seconds, how far did B move? Well, it was going 30 metres per second for each of those 10 seconds, so it must have gone 300 metres. How did I get there? I multiplied this length, 10 seconds, by this height, 30 metres per second. I calculated the area of that rectangle. The area underneath was the distance travelled. That works even for the other bits. Have a look at A. At A, it took 10 seconds to get up to 30 metres per second. And the distance travelled is actually the area underneath here, which is half of 10 times 30. It actually travelled 150 metres here, where it travelled 300 metres there. And even the next section, C, the same rule is going to work. The distance travelled is the area underneath that curve. It's not an easy shape to calculate. You could make it into a rectangle and a triangle if you wished. The rectangle here was 5 by 30, which is 150. And the triangle here is 5 by 15 divided by 2. You could work out the total area here would give you the total distance travelled, but it has to be the total of that whole area. Likewise here, distance travelled is the area underneath that line. In fact, this rule, if you've done calculus, you'll know, this rule for area underneath even works if it's a curve, even if it's a fancy curved shape. And you would use integration to work out that area. Now, we've just talked about distance time graphs and speed time graphs. In one of the textbooks in Louis, there's actually an error when it talks about acceleration time graphs. Let me show you. Page 57 of Louis, at the top of the page are these four. Let me get my highlighter out. The top of the page are these four graphs. They're correct. This is a velocity time graph. Okay? So if it is stationary, then the velocity is 0. If it's moving at a constant speed, then the velocity is a constant. It's a horizontal line. If it's accelerating, uniformly means constant acceleration. If it's accelerating uniformly, then the velocity increases in a line. If it's decelerating uniformly, velocity decreases in a line. Those four are correct. At the bottom of page 57 appear these four graphs. Now these four graphs are acceleration time graphs. Again, the first two are correct, but these two aren't. For a stationary object, it's not moving and it stays not moving, so its acceleration is 0. If it's moving at a constant speed, that's this one, then again its acceleration is 0. The slope of this graph is 0. Its velocity isn't changing, so its acceleration is 0. But have a look at this. This one here is incorrect, as is this one. If you are accelerating uniformly, that means you're doing this. But the slope of that graph, the slope of this is a constant, a positive constant. It should be here, not there. And if it is decelerating uniformly, that means it's doing this. This line goes down, it's decelerating. The slope of this line, however, is a constant negative. It's not doing that at all. This original graph would be if the acceleration is increasing linearly. Decreasing linearly. But they said uniformly. A uniform acceleration will be a horizontal line on this graph.